This video is going to be about critical density. Using the cosmological principle and the theory of general relativity, it can be shown that matter can distort space and time. And depending on how much matter there is in the universe, depends on how much it'll distort space. And so there's three ways it could do this. One way, if there's a certain amount of matter in the universe would have a flat shape. Another way, you'll have a negative shape. And the last way, you'd have a positive shape. So you can differentiate between these three amounts of matter by, like, if you were to draw a equilateral on each universe. So in the flat universe, if I added up all the angles, they would add to 180. In the negatively curved universe, they would add up to than 180, or less than 180, sorry. And in a universe with a positive curvature like this, it would be greater than 180 degrees. But we can't actually draw a giant triangle in the universe, so we can't make a direct measurement of the shape of the universe. But based on the density of matter in the universe, we can build models and estimate what is the shape of the universe. So the density of the universe, which model applies. So if the universe has a flat shape, that flat shape will go on infinitely in all directions. And the matter in this universe would expand infinitely and never return to its original position. If the universe is negative, which is sometimes called an open universe, so if the universe has a negative curve, it's also called an open universe. The universe's surface is flat, but it curves like a saddle, which goes on infinitely in all directions. The matter in this shaped universe would also never return to its original position and continue to expand outwards. The last model is of the positive universe, positive curvature. In this situation, the matter would stop expanding one day and return to its origin, which is why this universe's shape would also be called a closed universe. Okay, so the density of matter, which would be the density it has to have for it to be a flat universe, is what we call the critical density, which I'll represent with rho subscript c. And so when rho subscript c is equal to the actual density of the universe, it's flat. When the critical density is greater than the actual density of the universe, we have an open universe or a negatively curved universe. And when the critical density is less than, or when the actual density of the universe is greater than the critical density, we have a closed universe. All right, let me write all that out on a new sheet. The critical would keep the universe flat and infinite if that was the true density of the universe. If the density of the matter of the universe would be enough to provide a gravitational force to keep the universe from running away, but not enough to pull it back to its original position. In other words, in a flat universe which has the critical density, matter would expand until it reaches infinity and comes to rest. If we had a situation where the critical density was less than the actual density of the universe, if we had a situation where the critical density was greater than the actual density of the universe would be open and infinite. It would never stop expanding because there wouldn't be enough gravitational force to bring things to a rest at infinity. If our critical density was less than the density of the actual universe, then we'd have closed. The gravitational force would be strong enough between all the matter to pull it back to its origin. So how dense would the universe have to be at the critical density? Well, to be at the critical density, the critical density that we've calculated for the universe to be flat is 10 particles per meter cubed, which the average density of the universe is actually close to this value. This agrees with this video where I showed you that the boomerang survey data predicts a flat universe. All right, that's the end. Thank you.